Okay, so let's go through like a real problem like you might encounter in the real world. Walking around, you ask yourself this question. So let's say that we have a cantilever beam and it's 2 meters long. And the cross section is 5 centimeters across and 10 centimeters up. And we'll use the coordinate system we always use for beams. X-axis this way, y-axis this way. And we want to analyze how likely it is. This is steel. And we want to know how likely is it that this is going to break. So we want to calculate the principal stresses and the max shear stresses at the point where they're the highest. Where they're the greatest. Okay, so that's a pretty, it's pretty easy to imagine a case where you'd want to calculate something like that. And so we're just going to go all the way through, calculate the internal loads, try to figure out where we're most concerned about the stresses being high, and then calculate the stresses at those points. We might have a couple of candidate points, but we're going to try to figure that out. Okay, so the first thing we have to do is calculate the external loads at the wall. So free body diagram. There's a force vector here. I'll call that RA. There's a couple. And then we need the weight. So to get the weight, we're going to use the density of steel, and we know the volume of this thing. So the mass is the density times the volume. We run into the problem in these classes a lot where we don't have that many letters and we have a lot of parameters. So this row means density. It doesn't mean the vector from the about point to the place where the force is applied. And the density of steel is 7,000. The volume of this beam is 2 meters times 0.1 meters times 0.05 meters. And that gives you, I didn't write it down, 70? I think I remember that. Yeah, but that was a different row. If you answered this, then you were wrong. Okay, 70 kilograms. And so the weight force is 70 kilograms times 9.81, so 680, 6.7. I think that's right. Okay, so now Newton's second law says RAX, RAY plus 0, negative 686.7 is equal to zeros. So the force at the wall is 0 for X, and positive 686.7 for y. And then the moment equation, I'll put the about point at the wall. There's no moment from RA. There is this couple, I didn't name it before, but call it reaction moment. So there's MR. And then what's the moment arm for this force of 686.7? Yep. So moment arm of 1, force of 686.7, and then clockwise or counterclockwise? Clockwise, so it's negative, right? And so MR is equal to positive 686.7. This one's newtons, and this is newton meters. Okay, and now we're going to calculate the internal loads. So let's go back up here to the original, well, actually, let's go back to a new free body diagram with all of these forces drawn in. Remember that it's going to give you the wrong answer if you treat this like it's a beam with a force acting at the midpoint. You have to treat that as a distributed load. So in order to choose the right number of cuts, I'm going to draw this the way it really is. We have an upward force of 686.7. We have a couple of 686.7. And then we have a distributed load representing the weight. To calculate that distributed load, it's going to be the total force of 686.7 divided by 2. So what's that? 343.35. That's newtons per meter. And now let's think about where the subfunctions for these internal loads can change. The endpoints. And now, in between the endpoints, is there anywhere else where there's a point load or a distributed load function changes? Nope. So n is equal to 2. We only need one cut. Okay, so our first cut, our only cut, is valid for all x's between 0 and 2, the whole length of the beam. On the left end, we have the upward force of 686.7. And we have the couple of 686.7. And then we have the distributed load representing the weight. That's uniform, so that's 343.35. And then we have the internal loads, T, B, M, and I'm going to leave out torque for now in this problem because there's nothing producing moments about X. And before we can do the calculations, we have to represent that distributed load as a point force. Those uniform distributed loads, the centroid, the place where the point force acts, is right in the middle. So I'll redraw this. We have the upward force of 686.7. We have the couple of 686.7. We have the internal loads. And now the distributed load, the length of this is x. So we have a downward force of, the area of that rectangle is 343.35 times x. So 343.35x. And it acts right in the middle. So for dimensions, this is x over 2, and this is x. Okay, so now Newton's second law says 0, 686.7 plus 0, negative 343.35x plus p negative v is equal to zeros. So there's no internal tension. And v is equal to 686.7 minus 343.35x. And then the moment equation, we have the couple. That's a positive couple of 686.7 at the left-hand point. Then we have a moment arm of x over 2 with a force of 343.35x. And that weight force, is that clockwise or counterclockwise? Clockwise, so negative. Then we have the internal bending moment, so plus m. And then the moment from the shear force, so minus Vx is equal to 0. So m is equal to Vx. Yes. That's right. Okay, yes. So Vx plus 171.68 x squared. And then minus 686.7. And so now Vx, we have this expression for V, so we'll multiply all that by x. And so with the x squared term, we'll get a cancellation, and we get negative 171.68 x squared plus 686.7x minus 686.7. And this function is valid over the whole beam. So on the whole interval from 0 to 2. Okay, so let's think about what these look like. When do we not say they're valid? Like on the they're not. It's true that none of these are valid on the endpoints of the interval. That doesn't really matter to us because. But let's say we did that. All I'm saying when I say where is this valid is I'm just reminding you what this cut represents, you know. But as far as like the 0 and the 2, mathematically, you know, it's not valid on those 2 points, but intuitively, like for using this practically, I guess, we're still going to use these functions at those endpoints because a single point doesn't mean much to us. We're more looking for trends in how this thing is changing as you move towards a point. Okay, so what do these functions look like? There's no tension anywhere. Then the shear force, if that's 2 meters, starts out at positive 686.7. And when x is equal to 2, v has to be 0. So that's supposed to be a line. And then for the bending moment, so let's think about, so when x is equal to 0, we have a bending moment of negative 686.7. When x is equal to 2, this all comes out to be 0. And the leading coefficient is negative, so it's concave down. So it's going to be a parabolic shape like that. Okay, so now we have to think about, well, that's the internal load problem. Anybody have any questions about that? So now, if you're lucky, you can identify a point or a couple of points where you're concerned that the maximum stress might be. In this case, it's pretty clear. The points with the greatest failure risk are at x equals 0, right at the wall. Okay. This one turned out to be a pretty easy one to interpret because the maximum absolute value of shear force is at the same point as the maximum absolute value of bending moment. If you had a problem where this did something like that and your bending moment, you know, started here, and that would be more difficult. You'd have to analyze a lot more points, you know. Or sometimes you can do it mathematically, but in this case, it's pretty clear what x value we want to look at. But that does not yet determine what points we want to look at. It tells us the x value, but we still have to figure out what y values.
Are we assuming that it's mounted to the wall in a way that it's not going to pull out from the wall? Just depending on how that's structurally put in
there. Yeah, so I guess we're only looking at the beam. We're not exactly looking at the method that it's fastened. We know the x value. What y values? we could also ask ourselves, what z values are we concerned about? But since all of this is assumed to be symmetric about the, along the z-axis, about the y-axis, there's no reason to believe that any z values would be any different than any other z values. So there's a couple ways we could do this. We could look at points as a function of y, do these calculations of the stresses, in terms of the parameter y, or we could just take a few points to look at. Let's do this where, so we're going to calculate the stresses as functions of y. And then our final answer will have a y in it, and we can, find where that's maximized. Anybody have any questions about where we're going now? Okay, so our total stress is equal to the stress tensor due to the bending moment plus the stress tensor due to the shear force. There's no torque and there's no tension, so that's it. So let's start with the bending moment. Let's first think about the restrictions for the stress due to bending moment and make sure that we can get good answers for this problem. What are the requirements for a beam, for stresses in a beam due to bending? Yep. Right? Good. So straight, prismatic, and symmetric about y. So we have all these in this case. And in that case, what element of stress is bending going to affect? XX, that's right. So, well, we're always going to use the same coordinate system. So,
technically, if the coordinate system is drawn differently,
yeah, but let's just always draw it the same. Okay, so sigma XX is equal to negative my over I. The area moment of inertia is 1/12 times the width of the base, 0.05, times the height, 0.1 cubed. Could someone calculate that? Times 10 to the minus 6, and that's meters to the fourth. Okay, so at x equals 0, sigma xx is equal to negative bending moment at x equals 0. So that's negative 686.7 times y. We're going to leave that in as a parameter. Divided by 4.16 repeating times 10 to the minus 6. And can someone calculate that? 8? Wow, that's a lot. And we still have the y. Okay, so this is the stress in terms of y. Now we can plug in a y value to get an actual stress for that. That y value, you know, this y value, what's the range of y values we're going to be dealing with? Negative 0.05 to positive 0.05. Okay, because you can have a y that's below the neutral axis and a y that's above the neutral axis. So this is for y's in the range of negative 0.05 to positive 0.05. I guess this is inclusive actually. Yes, because remember at the center of the beam on the neutral axis, the reason it's called the neutral axis is because the length doesn't change there. And if there's no deformation, there's also no load. Okay, so now let's think about the stress due to shear force. So first we have to make sure that our calculations make sense. What are the restrictions for stress due to shear force? So this one I didn't really, instead of giving it in terms of like restrictions, I actually gave it in terms of the only two shapes that we can deal with. So rectangular cross sections, or circular cross sections. And if it's circular, then we have even more problems. With a circular cross section, we can only calculate the stress along the neutral axis. This is rectangular though, so we're good with this. So all of our calculations should make sense in this case. For this calculation, what element of the stress tensor are we going to get? XY, yep. So tau XY is equal to negative VQ over IB. Which of these values that go into this calculation are going to depend on Y? Any of them? V won't, right? I mean, we have just for X equals 0, we just have a fixed shear force. I and B won't. Those have to do with the whole cross section. But Q will. Remember, when you're doing that Q calculation, you choose a horizontal line to do that calculation for. Okay, so let's calculate Q. And for our cross section, here's the neutral axis. And we're going to do it for a line that I'm going to call Y. And let's think of VQ. So that Q is always positive. let's think of it on the top half, and then we'll think about how to apply that to the bottom half. So we're going to assume that this y is going to be positive, and then I'll think for a second and think about how to. I think maybe it's just we're going to get a value for just absolute value of y. Okay, so Q is equal to the area above that line times the distance from the neutral axis to the centroid of that shape, that area. The area is going to be 0.05, so this distance is 0.05. Minus y times this distance, which is 0.05. And so you get 0.0025 minus 0.05 y for the area. And then the distance is going to be so the distance from the centroid of this to here, you can think of that as the average of y and the top. Okay, so that's going to be y plus 0.05 divided by 2. Or 0.05, nope, 0.5 y plus 0.025. And now we have to multiply those. So Q is equal to 0.0025 minus 0.05 y times the quantity 0.5 y plus 0.025. Okay, so this is equal to 0.00125 y plus 1, 2, 3, 1, 2 plus 6.25 times 10 to the minus 5 minus 0.025 y minus 0.00125 y. Nope, that one doesn't have a y, right? This one's y squared, right? And this one's y. Does that look right? Okay, let me rewrite this. So 0.025 y squared. Ooh, those two cancel out. So is that what I got here? 0.025 y squared plus 6.25 times 10 to the minus 5 for Q. Okay. And now tau xy is equal to this. That's V. or that's Q, times V is positive 686.7. Need the negative. And then divided by the I that we got last time, that's 4.16 repeating times 10 to the minus 6, I think. What? Which one? Oh, okay. Yes. Yes. It should be. Okay, this is negative. The I that we got before is 4.16 repeating times 10 to the minus 6. B is the width, so that's 0.05. And could someone calculate that out? So just give me the two terms.
Times 10 to the 7th y squared times 2.06 times 10 to the 5th.
The positive fifth?
Yeah.
Okay. Anybody get anything different? This is y squared. Anybody else do it? Match one of those? Someone confirm one of those, and then we can move on.
0.25 times y to the second minus 0.0025.
Okay, so far all three of ours are off by a factor of at least 1,000. You got a different power? Oh, nice. Minus, okay, so that's right. All right, great. So now the total stress tensor is, so for the bending moment, we got 1.648 times 10 to the 8th y, and then zeros. And then the stress tensor due to the shear force is 0, then 8.24 times 10 to the 7 I squared minus 2.06 times 10 to the 5th, then 0. Then symmetry gives us this again. And so our total stress tensor is 1.648 times 10 to the 8th y, 8.24 times 10 to the 7th y squared minus 2.06 times 10 to the 5th, 0. And then symmetry says this is the same thing again, 8.24 times 10 to the 7th y squared minus 2.06 times 10 to the 5th, and then zeros everywhere else. Okay, so Now we want to look for some trends. We could calculate the principal stresses in terms of y if we do it algebraically. Your calculators might do that. I don't think I've ever tried that on mine. We could just use the equation from the eigenvalue problem and find principal stresses in terms of y. That would probably be sort of a pain. Well, let's try to get a sense. So let's think about how these vary. Okay, so let's say that this is sigma xx versus x going from 0 to 2. Not 0 to 2. We're only looking at the y values. So this is 0.05. And it's a linear function. And I suppose we should consider the other direction too. So what do you get if you plug in 0.05 for y? I want my vertical axis. Yeah, that's a little confusing, but I think this is what I want. Well, yeah, call it y.
0.
What?
0.
For what?
For y.
For this, so
that.
For the xx. So it'll be 0 for y equals 0, and we know that about bending, stresses due to bending. Okay, so this is 8.24 times 10 to the 6. So this one is negative 8.24 times 10 to the 6. And then let's do the same thing for the shear stress. This one is going to be, there's no difference between negative and positive values because we're squaring that y. So this one's going to be symmetric about the y-axis. So here's 0.05. Here's negative 0.05. And you said at the two endpoints it's going to be 0. It has to be with stresses due to shear. So we got that and that. And then what's the value, I guess, when y is equal to 0? We're at negative 2.06 times 10 to the 5th. And it's a parabola. Okay.
Where are you getting the one? See.
All right, so we have the basic trend that we always have when we have stresses due to bending moment and stresses due to shear force. The stresses due to the shear force have to be maximum absolute values at the neutral axis. That's where the stress due to bending moment is is 0, and then absolute value of the stress due to bending moment is maximum, where this one is 0.
How did you get the 8.24 e to the 6?
That is just from plugging in 0.05 for y. Oh, for this one, that is just, that's plugging 0.05 in for the x-axis equation.
I just do 10 to the 8 times 0.05.
Yeah, 1.648 times 10 to the 8th times 0.05.
In the exponential area.
In the what?
Exponent area. So you're putting 10 to the 8th in that same upper subscript.
Right.
Doing times 0.05.
Yep, that's right. Okay, so now we want to figure out, I don't think this really tells us, this doesn't really give us a point to look at yet. What we sort of have to do is we have to take into account, so we're trying to figure out where, for what y value, we're worried about this thing fracturing, taking into account that we're most concerned about fracture due to bending at negative and positive 0.05, and we're most concerned about fracture due to that shear force here. The fact that these are different by more than a order of magnitude says that we're going to be more concerned about fracture due to the bending moment, and so if we calculated if we did this all as a function of y and calculated the y value where like the principal stresses were biggest, it's going to be somewhere closer to it's going to be somewhere closer to a y value of 0.05 because the effect due to the bending moment is so much bigger than the effect due to the shear force. So for our purposes, let's just think, let's just figure out what the values are here and here, and we'll pretend that this isn't here at all, okay? Really, it would be a point a little away from there, but we're gonna say that this is a pretty good guess for where the stresses are gonna be high. Anybody have any questions about that thought process? All I'm doing is saying the biggest this one gets is something times 10 to the 5. The biggest these get is something times 10 to the 6. I'm going to be more concerned about this one.
So we're more concerned with the magnitude instead of the actual.
Well, if they were the same order of magnitude, then we'd have to think about where in here, both of those are contributing to the stress in a way that gives us a maximum. And the only way to do that really would be, we could guess that it's halfway between, or we could calculate the principal stresses in terms of y and then do it algebraically. Yeah, so, right. So we'd actually have to write out that eigenvalue equation, come up with a huge, yeah, but I mean, you could do it with a computer. But in this case, since those maximums, absolute values, are so different, we know that it's going to be somewhere close to where this is a maximum, and so we'll just use that as our estimate. So, no, this is everything. Here's where this. Okay, that's more important than finishing. I'll finish this next time. But you'll have to do something like this all the way up to calculating the internal loads and then using those internal loads to calculate the stresses at a given point. But what I did differently here was I kept it all as a function of y to try to see analytically where it was going to be a maximum. And in the last step, it got sort of messy. All right, any questions?
So if we put on the quiz,
Mm-hmm.
sigma